Swayam Prabha. Digital India. Educated India.
Welcome back, everybody. We are going to talk about NMR spectroscopy. We have two different NMR spectroscopies combined, a carbon-13 and a proton NMR. So we have 4 spectra here for you. Actually, we have 4 sets of spectra. And they all have the same molecular formula, which is C4H9Br. So they're just isomers of a C4H9Br. Let's look at it. Let's do it stepwise. 1, do the omega, and that is going to be 2 times 4 plus 2 minus 9 plus 1. That's 10 over 2, 0. No double bonds. Let's look at then the carbon-13 NMR and see how many lines there are. Each line corresponds to a carbon in a unique environment. Here you have 1, 2, 3, 4. So all 4 of these carbons are different. You don't have any symmetry in this molecule. As I said, for 13 carbon, the integrals are not very reliable. So even though you have 4 carbons, you can see how one of this is really much shorter than the other, you see. So you can't really tell from the height how many carbons are buried underneath each peak. So this is 40. Therefore, almost all of them are in the alkyl region. And you can say that, you know, this kind of reinforces it. There is absolutely no unsaturation there. So the carbon-13 NMR provides us with some very valuable information. 4 different carbons, and each one of them is in its own unique environment, and it gets more and more de-shielded as you go downfield. That's pretty much what we know. So therefore, you don't have any symmetry inside the molecule here. No symmetry. Therefore, we are going to then look at possibilities now using the proton NMR to figure out the exact backbone for this isomer. Let's start with the proton NMR now. We have 4 peaks. Let's write down the ppm values, the multiplicity, the number of hydrogens below each one using the integral, and also how many neighbors do we have, just like we've done before. A, B, C, D that's got 4 different environments, and you can see that the C13 details are the exact same thing, 4 different carbons, which means each carbon is in a unique environment, and so the hydrogens also are giving 4 different peaks. So these really nicely corroborate each other in terms of information that you can gather from the data, okay, from the graphs. All right, so A delta is about 0.9 ppm. We're just being a little approximate here. This is about 1.5 ppm. This is 2.0, and this is about 3.6 ppm. Let's look at the multiplicity. This is a beautiful 1, 2, 3 triplet. This has got 1, 2, 3, 4, 5, 6. And so that is going to be a nice sextet. And here we have 1, 2, 3, 4, 5 mountain peaks, and that is going to be a quintet. This one is a triplet. So we have seen triplets before. Triplet means, well, T for triplet. Let's look at the heights here and find out how many hydrogens are buried in this beneath this peak. That means in identical environments. This is 3, this is 2, 2, and 2. So 3 centimeters, 2 centimeters, 2, and 2. Well, number of neighbors, n plus 1 is the multiplicity. And so in this case, we can figure it out. N plus 1 is a 3 because it's a triplet. N therefore is 2. It's just 1 less than the multiplicity. Sextet, n plus 1 is 6. Therefore, N is going to be 5. N plus 1 is a 5 quintet. N is going to be 4. 4 neighbors, 5 neighbors, 2 neighbors, and this guy is a triplet. N plus 1 is 3. Therefore, N is 2. This guy's got 2 neighbors. He's got 2 hydrogens with 2 neighbors. 2 hydrogens, 4 neighbors. 2 hydrogens, 5 neighbors. 3 hydrogens with 2 neighbors. Let's look at what are the possibilities when you have isomers for C4H9Br. You can have carbon, 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 and a bromine here, or you could put that bromine here. You could have carbon, 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 and a bromine here. Now, if you branch this up, then you will not get 4 unique carbons. The only way to get 4 unique carbons is if they are in a row, and they are different distances away from the bromine. So this guy is probably going to be the one right next to the bromine. Okay, so those are the 2 possibilities for 4 different carbons for this formula. If you take the bromine and put it here, it's going to be the same as this. And of course, if you take the bromine and put it here, it's going to be this. So those are the only 2 possible isomers that give you 4 different carbons. Let's look at how many possibilities are here for these protons in terms of splitting with the neighboring protons. So which is A, B, C, and D. Before we do anything, we know bromine is the most electronegative group, and due to inductive effect, it's going to pull harder or tug harder on the first carbon's electrons, and it will deplete the electrons around that carbon, which means it's going to pull electrons from the hydrogen, and both of these would be the most d-shielded. And the inductive effect falls off with distance. So therefore, most d-shielded, the second most, third most, and the most shielded. And that's what we have, all in a row. And we have 4 of these, and you can pretty much predict the same. Let's see if our prediction's correct. Let's label them just according to the delta values. The more d-shielded would be the one next to the bromine. That's a D. Then C, B, and A. So let's see if it's going to correspond to these peaks. So just based on the delta, can we assign this? And for the 13 carbon, the same. Let's say this is your D carbon, C carbon, B carbon, and A carbon. So this would be D, C, B, A. And why is C so much smaller than the others? Again, the integration and the peak height of the peaks on a C13 really don't correspond to the number of carbons under each peak. So that information is not there. We just have to base it on the delta scale over there. All right, let's see if this is correct. Does it corroborate what we have according to your delta values? Let's check it out. So this would be the most d-shielded. It's a triplet, and you have 2 neighbors. So 2 plus 1 is 3. That's your triplet. This guy, the HC protons, have 1, 2, 3, 4 neighbors. 4 plus 1 is 5. That would be a quintet. HB has got 1, 2, 3, 4, 5 protons. So 5 plus 1 is 6. That's your sextet. This is going to be 2 plus 1 for A, HA. All of these HAs are seeing the same number of protons here on the B. So you can have 2 plus 1, 3. You can have a triplet. So HA is a triplet. Very nice. That's correct. HB, sextet. There you go. HC, quintet. And HD, triplet. So you could have based it just off of the delta values. But it's really nice to see that the splitting patterns tell you the exact same thing. And it's corroborated again by the 13 carbon spectra. All right, let's move on to this isomer here. How many peaks do we have? 1, 2, 3, 4. So therefore, it has to have 4 carbons in 4 different environments. How many carbon-13 peaks are you going to see for this? That's right, 4. Let's see, 1, 2, 3, 4. And it is different from this. This is 60 to 40. So this is about, you'd have something around, let's say, 53 or 54. You are having something around 38. You have something around 25. And you have something around 16. This means they're all below 80 and they're mostly all alkyl protons. If you have alkenes, they're going to be in this region and we don't see anything here. Therefore, they're all alkyl protons. Again, that's what our formula is telling us. We don't have any double bonds. Let's look at the C13 and your NMR. Well, obviously, 53, that's your most D-shielded. Therefore, bromine is probably sitting on that carbon. This is next to that, then next to that, and this. So what are the possibilities for 4 carbons in different environments? We said one was this, and let's look at the other one. Let's look at our NMR. So we got 4 peaks here, A, B, C, and D. So we're going to write this over here and look at all of the values for that. And delta ppm for these are going to be about 1.0. This is going to be about 1.7, 1.9, and this is going to be about 4.1. And let's do the multiplicity. We can see how useful that information is. 1, 2, 3 mountain peaks. So that's a triplet. This has got just 2 and it's very tall. That's a doublet. This guy has got 1, 2, 3, 4, 5 quintet. And this is going to be 1, 2, 3, 4, 5, 6. That's a sextet. All right, so that's going to tell us the neighbors. Let's look at the number of hydrogens in here. Let's look at the height. 3 centimeters, 3 centimeters, 2 and 1. So the centimeters correspond perfectly to the number of hydrogens. So this is 3, 3, 2, 1. And I should thank John for blowing it up so perfectly. All right, let's look at the number of neighboring protons for each one of these. A is a triplet, so therefore n plus 1 is 3, n is 2. This is a doublet, therefore n is 1. This guy's got 1 neighbor. Quintet, and therefore it's got 4 neighbors. And sextet. It's very busy over there. It's got 5 neighbors. Let's look at what a possible structure could be for this. So this is probably a CH3 because they all have the same environment. Another CH3, a CH2, and a CH. What do you think, guys? So the CH here is the most D-shielded. So therefore, you could say that you would put the bromine right there. So 1 hydrogen there, CH. Where would you put your CH2? Well, it's either this side or this side. Let's try on this side, CH2. You have a quintet for this. Therefore, if you have a quintet and you have 4 neighbors, you have 1 here, and you probably have 3 here. So therefore, you are going to have 3 plus 1, 4 neighbors, giving you a quintet. 2 hydrogens giving you a 2 plus 1 triplet. So here's triplet, 3 hydrogens, quintet, 2 hydrogens, and that's probably this, and your triplet here with 2 neighbors. All right, the sextet has got 5 neighbors. Let's see, 1, 2. Where would you put the other 3? There's only 1 opening here, and that's here. So this is not a symmetric structure. Each one of these carbons is unique, and so you get 4 different peaks. And over here, this is going to be a CH3 triplet, and so these are your triplets here, HA. This is the only one that could have a triplet because it's got two neighbors. Over here, this CH3 has got only one neighbor, which makes sense because you only can have this CH as a neighbor for this, which means these are your HB protons. This is your sextet with 5 hydrogens, so that is your D. Does that make sense? Let's check it out. So that's going to be your most D-shielded. So 5 hydrogen neighbors here, giving you a sextet, and you can see it's at 4.1 around, most D-shielded because it's directly attached to the carbon that's connected to the bromine. This is the most D-shielded. And just like here, this would be your most D-shielded. Over here, these two you would expect to be quite close to each other just because they're equidistant from the bromine. And that's why you can see they're both very close to each other. Doublet, 1 hydrogen neighbor, and it has got 3 hydrogens beneath it, and this is your HB. And this is your sextet, and it's got 1 hydrogen underneath that. So this perfectly corresponds to your NMR. And what would you predict in terms of your C13? Who's 53, you think? Obviously, it's going to be the guy over here. Let's label these the same as that. D, this is going to be your CD. This is going to probably be C and B over here. So CB, and this is CA. Now that takes care of these two, and you can see if you have 2 spectra, it only adds a lot more information, and you can just go between the two and give an exact structure for the isomer. Let's look at these 2 spectra over here. This spectra over here has only got 1, 2, 3. CDCl3, again, as I said, would be the standard, and it's at 77. Anytime you have CDCl3 on an C13 NMR, it's going to be at 77 ppm for that carbon. So you can see they all show up. So you don't count that, or the one at 0. You count the other 3 inside. One is a lot taller than the other. Let's look at the peaks. 3 NMR peaks. So that shows that there is some symmetry. All 4 are not in different environments. What are the possibilities for having 3 different types of protons? So now we probably would have to branch it up. So what are the possibilities? Well, we've done a straight line structure. Let's branch it up. So let's take this carbon, and instead of attaching it to this, let's attach it to that. Now, there are lots of possibilities now if you do that. So here's your C, 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 and now you're going to put a carbon here. As you can see, there is some symmetry here. Well, you can put your bromine here or here. Putting your bromine here, here, or here would be the same. So let's put your bromine here to start with. So, and let's see, what we can get. Let's put our hydrogens here. And then we will label these according to your NMR. All right, so there you go. You can see that these 2 carbons are identical. You have that's your structure. You have a mirror plane of symmetry there. So these 2 are the same. This is in a unique environment, and this is in a unique environment. So you only have 3 different types of environments for carbons as well as hydrogens. These 2 carbons are in identical environment. They're equal distance from this bromine. Okay, and that is what you see here. Now 3 peaks. 2 of them are identical. And they're furthest away from the bromine, so you will have them closest to the 0. This is probably this carbon that's directly connected to the bromine because it's de-shielded, and maybe this one is this. Let's check it out with the proton NMR. We have again 3 different peaks. This is our TMS, which you don't really have to worry about. So A, B, C. Let's look at the multiplicities and the delta. Delta for this is going to be 1.0. This is going to be 2.0. And this is going to be about 3.3. Let's look at the multiplicity. This is a very tall doublet. And this is a multiplet. And this is again a doublet. All right, let's look at how many hydrogens are buried under each one of these. Let's count it out. This is going to be 6. This is 1. And this is going to be 2. Matches exactly with the centimeter scale. So the heights here, 6 to 1 to 2. And it adds up to the 9, so the empirical ratio is the same as the molecular ratio. N plus 1 is M. Multiplicity, in this case, its doublet is 2, so N is 1. This has only 1 neighbor. This is a multiplet. How many neighbors do we have for a multiplet? We have no idea. Okay, so it is definitely going to be more than 6. Now, doublet, so again, N plus 1 is going to be 2. Therefore, N is going to be 1. So these 2 have 1 hydrogen as a neighbor. So they have a CH next to them. Doublet, and that means it's got 1 neighbor and it's got 6 hydrogens on it. How do you get 6 hydrogens in identical environments? We've seen this before. We saw this with isopropyl. That's right, doublet septet. But over here, this is going to be your isopropyl group. So let's try to assign this over here. You can see this is very, very symmetric here. Therefore, these 2 are identical. And that's the only way this isopropyl group with these 2 methyl groups can have 6 hydrogens in the same environment. So these are probably A. And what would you expect for A in terms of multiplicity? How many neighbors does it have? Has only 1. So 1 plus 1 is going to be 2. All these 6 hydrogens are going to be a doublet. And that's what you see, doublet. Well, here is a hydrogen that has got 6 neighbors and 2. That's 8. So that's going to be like a nonet, which you really can tell in maybe like a 300 megahertz instrument. So they're all collapsing into a multiplet. And that's your multiplet 1 hydrogen, that's B. This has got only 1 neighbor here. This is your 1, 2, 3 bond coupling here. 1, 2, 3. Therefore, this is going to be also 1 plus 1, 2, a doublet. Therefore, you can see this is going to be a second doublet with 2 hydrogens on it, HC. Pretty much everything falls in place here. And what would you predict for your C13? Well, you have 2 Ca carbons, and they are the most shielded because they're away from bromine. And that's why you see a very tall peak here. That's your carbon A. This is going to be your most de-shielded. It's right next to bromine. This is going to be your carbon C. And this guy in the middle is probably this one. And as you can see, these you would expect to have a 1-to-1 ratio, but the integral on the carbon 13 is not reliable. So you cannot really, say that that ratio here corresponds to the height, unlike in a proton NMR. Let's look at this spectra here. One peak, that's it. Well, actually, there's a little teeny one here too. So there's 2 peaks there, and 1 peak on the NMR. How would you get all of the hydrogens? How many hydrogens? There are 9 hydrogens underneath this peak. So the peak is, there's only 1, and it's at 1.9 singlet. There's no multiplicity here. 9 hydrogens. Okay, well, how do you know it's 9? It's probably going with the TMS. So we know there's only 1 peak. So we know all 9 are here. Now, neighbors, let's see. If you have a singlet, n plus 1 is 1, n is 0. This guy is quite peaceful all by himself. How would you get an environment where 9 hydrogens are identical? So you have a carbon, and you have to have all these carbons being equivalent. So let's see. If you put hydrogens on here, you will get 9 hydrogens, which means there's only 1 place to put that bromine. Where do you think your bromine is going to go? Right in the center here. You do have, let's say, 2 types of carbon 13 NMR, because you have this carbon, and then you would have these 3 being identical, because, you know, it's symmetric. So therefore, this, well, you have symmetry here. So therefore, you are going to have this being this teeny peak here, and all of these being this tall peak here. So if I label these A and B, this is going to be your CA, this is CB. As you can see, the height ratio is not reflective of the carbon ratio. This one, all 9 in the same environment, when you rotate this, they're going to be identical. The machine won't be able to tell them apart. They are all exactly in the same environment. They are all equidistant from that bromine. Therefore, they have the exact same delta value, around 1.9. In summary, I'd like to say that if you have an NMR for your proton and an NMR for your carbon, that's all you need to figure out a molecular structure for a molecular formula. In this case, you have multiple isomers, and you can say them apart just by using these 2 pieces of data. We didn't have a mass or an IR because we really don't need it. The delta values on the C13 and the proton lets us know how de-shielded the carbon is, and probably what is in the neighborhood in terms of a functional group. Now, if you have all 4 different environments, you can see you get 4 different peaks on your C13 in these 2 cases. If you have symmetry, you will see that they will collapse into fewer peaks on your C13. Now, you don't always need to have the same number of peaks on your carbon 13 and proton NMR. Not necessarily. Proton NMR sometimes may have more peaks. Even the proton NMR would go from left to right in terms of de-shielding. All right, guys, if you have any questions, don't hesitate to let me know. The only way to master NMR is to do them. Do them over and over again, and you will see the patterns emerge. Sec bureau, bureau, isobureau, and third bureau. We'll see you soon with more isomers. Stay tuned. Talk to you soon. Bye.